So there's probably a lot of different backgrounds of people that are taking this right now, and I'm going to try to address it to all levels. I don't want to be too high level, and I don't want to be too low level. So maybe people can let me know afterwards how that went. Presumably, people have gone through the Fast.ai course 1, the Practical Deep Learning for Coders. But I know how that goes. Sometimes going through that course can mean just watching the videos and not doing anything else. And so you're familiar with a lot of the material, but you really haven't. You might not have tried anything or actually worked with some of the notebooks. So in this set of reviews, I'm going to urge everyone to really use the notebooks as much as possible. And to do that, it's really all about infrastructure. You need to set up your infrastructure for running the notebooks. Now, you can either do it on your own. Let's see. Go forward a little bit. You can run the notebooks on your own computer by there's a couple of good web pages that I found for doing that. One was by a Medium article by Pierre Guilou, how to install Fast.ai version 1 on Windows 10. And I'm working on Windows 10, and this seems to work for me. Although I know that the last 2 lessons, which are going to be the Swift lessons, I'm not sure I'm going to be able to run them on Windows 10. So I might need another solution by then. And there's also the official installation guide on the Fast.ai GitHub. And so what I did was I basically used both of these together, and that allowed me to get through the installation. And I think I have everything working now. Anyway, let me go. And then there's the other way, which a lot of people are going to do, is use the cloud. And on, in the introductory web pages for this class, they have a description of all the different ways that you can run the notebooks on the cloud. There's Cressel, Salamander, Gradient, Lloyd Hub, Kaggle, Google Cloud, Colab, and all that. So those, and there are links to the instructions for all of it. So if people need to do that. Okay. Go up. So the overview of the course is, there's going to be lessons running 8 through 14. 8 through 12 are the Fast.ai and PyTorch lessons, and then we'll start the last 2 lessons will be Swift. I'm going to go through and mute all the participants right now. Although if you need to say something, you can unmute yourself. Okay. Can everybody hear me, or can people hear me now? Just I want to make sure that I'm still being heard. I'll look at the chat. Okay. Okay. I guess I should have waited a few minutes because people are starting to show up. So, okay. Okay. I'll wait till 9:05 and then I'll start. We're starting to have got like 17 people so far. 18. All right. All right. So again, we're doing starting the review of the Fast.ai part 2, which is practical deep learning from the foundations. Let's see. Not being able to move. Let's see. Hold on for a second. Okay, the slides are all there. Somehow I lost. All right, so as I guess the key thing I wanted to say before we start is that you need to make sure that you have all the infrastructure in place for running the notebooks. That's the most important thing. So I devoted a couple of slides to that. Not that you'll be able to do it while we're in real time, but the idea is you can either set up your environment on the cloud so that you can run notebooks whenever you need to, or you can set it up on your own machine. And there are a couple of web pages that allow you that guide you in how to run and how to set up the Fast.ai environment on your own machine. These are for Windows 10. The first one is for Windows 10. The second one is more general, and it's on the Fast.ai GitHub. And so I've been able to use those two to get things started for me in Windows 10. Okay, just an overview of the class. Jeremy's idea is that we want to recreate Fast.ai library almost from scratch. And the rules are that you get to use Python and the Python standard libraries and non-data science modules. And you get to use PyTorch, but only array creation, random number generation, and indexing into arrays. And we get to use the Fast.ai data set so that we won't have to recreate those. And we get to use matplotlib, which is the plotting library and so on. No one wants to recreate that from scratch. So okay, so all right. So the idea is that Jeremy wants us to experiment with the notebooks, and by creating some of these functions from scratch, we'll understand them much better. And also in this class, we'll be delving into some of the papers, reading papers and so on. So he wants to sort of get everybody used to that idea. And okay, so the opportunities, which we should say up front, is that you could actually contribute to the libraries if you get into it that much. You can actually help to write the libraries. You can write blog posts on what you're learning, and you could, by experimenting with the notebooks, and you'll be able to do your own projects. So you'll learn a lot that way too. All right. For the first part of the class, the steps that we're going to go through are leading towards creating ResNet from scratch, the ResNet that he created in the first class. And of all of these steps, lesson 8 is just basically this matmul. Lesson 8a is just matmul. The one we're going to do today is just the matrix multiplication. And then lesson 8b, the rest of lesson 8 is forward and backward propagation. So that's sort of the overview of where we are and where we're going. We're heading towards creating ResNet from scratch over the first few lessons in the class. Okay, so Jeremy mentioned that a lot of people when you look at a paper, you're going to see something like this a lot of the time. There aren't any papers that are just text. They're all going to have equations in them, and they're sort of terrifying sometimes. And so Jeremy suggests that the first thing to do is to learn some of the Greek letters, because mathematics is always expressed in Greek letters, and if you don't know the Greek letters, then this is just going to be all gibberish. So it's important to find a website where you can learn the Greek letters and also the other mathematical symbols that are used. So there's a lot of different symbols here: summation, these double vertical bars, and so on. And if you run across symbols and you want to understand what they mean, you can always go to this website that Jeremy earmarked here. It's basically wikipedia.org. It's a list of mathematical symbols, and you can just scroll down and find the symbol that you want to understand. And it gives you not only an explanation of what the symbol means, but even the LaTeX for if you wanted to typeset that into a document. And then there's another. You can also go to Wikipedia to to look up Greek symbols. I found a nice little image that shows all the Greek symbols in one page. There's capitals and there's cursive, and the ones that are most often used in the papers are the cursive ones. And so here they all are. Basically, it helps to just learn the names of them, so that as you look through a paper, you can say, oh, alpha equals, you could identify the symbol as its Greek name, and that would be really helpful to learn the names of the Greek letters from something like this, a table like this. Jeremy also mentioned this really nice page called Detexify, where if you want to find the LaTeX for typesetting a mathematical symbol, you can go to this site called Detexify, and you basically just draw the symbol in this little box, and then it uses machine learning to tell you what it thinks the symbol means. And so you'd want to go to the one with the highest score. And so you draw this little sigma symbol, and the highest score is this one, which seems to be right in this case. Okay. So the next part is basically I'm going to try to go through the notebooks with you, but Jeremy has set up this sort of ingenious way to develop notebooks, and we have to understand what he's done. He's got this Python script called notebook-to-script.py, which you'll see in the directory on GitHub where all the notebooks live. And basically, this thing converts. Okay, so the first thing to know is that these notebooks, the very first notebook is called 00_exports.ipynb. The ipynb files are in some format called JSON, which is a text format. And Jeremy has written this script that takes that reads the JSON file format of the notebook and converts it into a Python module. So this command here, which is in the first notebook, Python notebook-to-script.py, on this notebook, converts it into a notebook and stuffs it in the exp directory. It converts it into it converts it into a module named nb_00.py and stuffs it in this directory exp. And the naming convention is nb_ and then the first two letters, or the first, I guess, whatever comes before the underscore in the notebook's name. So when you convert this notebook, you'll get nb00. When you convert the next notebook, which is notebook 01, you'll get nb_01. And so in each successive notebook, you import the Python module that was created from the previous notebook. And that way, every time you run a notebook, you have available all the material that came before it. So that's that thing that he's doing. All right. So one of the main ideas in this lesson is the idea of broadcasting. It's dealing with these tensors, these arrays, matrices, tensors. And broadcasting is sort of a cool way that extends array operation, the syntax of array operations by means of some implicit rules that need to be explained. But before we do that, we can look at this really nice example here. Okay, so if you're adding adding a 4x3, two 4x3 arrays, it's straightforward to just add them and get the result. But sometimes you might want to do something like add this row to every row in this array. And broadcasting lets you do that. You just say, I got this array, I'm going to add this array. Broadcasting implicitly knows that I want it to extend this into a 4x, basically multiple, copy the row 4 times, and then add it. And that gives me this implicit operation. And even more is that if you give it two vectors that are obviously not the same dimension, one of them is a column vector, one is a row vector, and you say add them, it will know that what you want it to do is to expand this one out by copying the column 3 times, and expand this one out by copying the row 4 times, and then add them like this and get the result. So that's an example of these implicit rules. There's a nice page that discusses these rules. Jake Vanderplas's GitHub. I found this basically a summary of it. There's only 3 rules that you need. And it has to do with padding the arrays so that when you do the array operation, they'll have the same number of dimensions. Anyway, so that's that one. Okay, so this is my last page, but what I want to do now is stop sharing these slides and actually go right into the notebook and start working on it. So I'm going to unshare my PowerPoint presentation, and I'm going to go and share the first notebook. Share. Let's see. Can people see this? My screen? I'm going to go into one of the notebooks. That's not the one I want. Okay, can people, am I sharing the first notebook? Can people see that? Somebody want to let me know?
Yes.
Okay, great, thank you. So I'll actually go to the 0th notebook, and so this is the 0th notebook, and all it is basically a little test. You just set up this variable test, capital T-E-S-T equals the string test, and this is just and then you run this export, and it writes this notebook 00.py, and here they're explaining a little bit about what's going on. The IPy-NB files are JSON format, and so you can actually look at the JSON, import the JSON file and look at its first cell, and it'll tell you what, you can sort of see what's going on in the file. And so I just added another, the idea with these notebooks is you treat them as little sandboxes, you play with them, so you don't just treat them as sacrosanct. So I just thought, let's look at this D, the whole thing, and I'll run this, and it shows me everything that's in this notebook. So it's all JSON. I'm not really that up on JSON. It's gibberish to me, but you can sort of see that it has a structure to contain what's in this notebook. All right. So next we'll go to the actual notebook for the lesson, which is notebook 1. Oh, and this is, by the way, this is the notebook to script.py, where Jeremy defines this function that he uses to convert the JSON, to convert a notebook into a Python module. So this is the function that he calls in the when he wants to convert back into the 00 notebook. This is that command where he calls notebook to script.py on this notebook, and it converts it into a module. And the module is all it's going to have in it, basically, that we're going to need is that we could play with is this test variable. So when we import that module in the next notebook, we should have this test variable, we should have it available to us. So that's just a little test. But anyway, so here we are in the, this is the main notebook for this is the main notebook for this lesson. And so what I thought we could do is just, since I have it set up on my machine, we'll just run through it. So this is the first cell that Jeremy puts in all of his notebooks, and it imports the matplotlib, and it also lets you make changes to your environment outside of this notebook and have those changes registered in the notebook. That's the first 2 lines. So I'll run that. Now he's going to report. Now he's going to import the thing that we saved, which NB underscore 00, and really remember all it has in it is the variable called test. But let's do that. Okay, so in this cell, he's setting up this comparison function called test, which compares two objects, and by means of some function which he calls CMP. So once he defines, and then it tries to test whether these two things are whether the whether the comparison is true. And so for an application, you could make this into an equals tester. That is, it tests whether two things are equal, and that's what he defined here, this test underscore eq. So you have A, B, and then the operator, which is this CMP thing, now becomes, that is the comparison operator, now becomes equal. And so he's defined this new function, test equal. So now the first thing we can do is run that. Well, make sure I ran that. And let's see, did the import work? Remember, we imported a variable called capital TEST, and we want to see if it, and that variable equaled the string test. Let's see if that worked. So since it didn't complain, that means it worked. All right. So the next thing he does is he gets the MNIST database for some things to play with in this notebook. So let's do that. Setting up the path, importing the data into a training set. Although we're not really going to do any training here. All we're doing this for is to grab some tensors. So now we have these tensors, x train, y train, x valid. All right, so let's see. You can see that so he's, let's see, this first line, assert n equals y train shape is 50,000. That is the first dimension of the shape is 50,000. N, let's see, where does n come from? Oh, there it is. N is the first dimension of the shape, and this just tests whether it equals 1,000. Sorry, 50,000. So does that. And the minimum of y train is 0. The maximum of y train is 9. We see those things. That's just those. He's using this test eq to this test eq function to test them. Okay. Not sure what this is. This is for image display. So does that. Get the first image. It's going to be some numerical picture. I guess you view the image this way, and so now you set up these arrays, and now the main part is just to demonstrate this matrix multiplication. And the first one is just the dumb Python way to do matrix multiplication. He set up this function matmul AB, which multiplies array A by array B, and the first thing you want to do is check that the number of columns when you multiply array A times array B, the number of rows in array A has to be the same as the number of columns in array B. So sorry, got that backward. The number of columns in the first array has to be the same as the number of rows in the second array. So that's this test here. Assert that's true. Then let's see. Now he's just making an array C to place the product, the array, the multiplication product in. So he's initialized. Basically, this is initializing. And the product of two arrays like this, the dimension is going to be the number of rows is going to be the number of rows of the first array, and the number of columns is going to be the number of columns of the second array. So that's why he initializes it this way. And so you can see what he's doing here. He's going through the rows and the columns and doing the matrix multiplication in the dumbest way possible, but it requires 3 loops. So that's the function defined. Let's see. What are we doing here? X valid. So now we're just making some arrays and looking at their shapes. Now we have two arrays that we can multiply together. See, we have 5 rows, 784 columns, and 784 rows, 10 columns. So there's the right, these arrays have the right relationship to be multiplied together. And he did this little calculation to figure out how many rows and how many total elements that the thing might have in it. But anyway, the main thing is to look at the time. It takes a whole second to multiply this way, and then we can see that we got the array. There it is. The next thing he does is he shows how to make this a little faster, because I guess the theme here is infrastructure. This multiplication is not going to do us any good if it takes a minute to multiply these moderately small arrays together. If it takes us a whole second to multiply them together, it's not going to be very useful to us. And so we're looking for a way to get a faster multiply. And so he now refactors the first array multiplication to a second form, where now you do the inner loop implicitly. So so the ij element of multiplying two arrays together is going to be the dot product of the ith row of the first array and the jth column of the second array, and that's what this is. The inner thing here. You multiply these things together and then you sum them. That's the dot product. So each element can be expressed as a dot product, and that makes things faster. So you run that, time it, so now it's speeded up quite a bit. It was a second, and now it's 2 milliseconds. Okay, so then he goes even further. He uses broadcasting. Oh, and then he invents this function, because when you want to test if two things are equal, there's a lot of round off and so on. So two things might be essentially equal, but if they won't be precisely equal, and so it won't show that they're precisely equal. If you try to ask, if you say is A equal B, it'll say false. So instead, he invented this function, test near. So to be near, for two things to be near each other, if they're within some tolerance of each other, then it counts them as near each other, and that's a useful test function that he invented that we can then use. So he can write this function, and we can the T1, remember, is the product of the first multiplication, which is the dumb Python way to do it, and matmul M1 M2 is the second way, which was using the inner product to eliminate one of the loops. So we want to see, are these equal? And since there was no complaint, that means they're equal. That's the way he defined these functions. Okay, so next. So next we can go through a little bit about broadcasting but we're going to progress through this notebook and get faster and faster matrix multiplications. That's really what the notebook is doing for us. I'm going to stop here and ask if anyone has any questions. You can unmute yourself and ask a question if you want. Don't be shy. Any question at all?
Hi, this is Christine. Can you hear me?
Yes, I can, Christine. Hi.
Hi, I actually had a problem at the very beginning with this new way of saving scripts, and I'm wondering if it was just because of the way I have my environment set up. I'm using Google Colab, and I was not able to get the system to register the names of the imported files that we created, the .nb files. So I'm just wondering if you have any advice for those of us who are using Google Colab, or if you kind of did some troubleshooting you want to share.
I had the same experience in Colab, and after a while I decided I wasn't going to use Colab, so then I did it so I don't know the answer to that question, but it might be that you need to import Fire. I'm not sure about that, but that's one of the steps that, because I think when I first tried these notebooks on my own computer, I had the same problem. It wouldn't export them. And then I noticed you have to, it doesn't say so in the instructions, but I found it somewhere else on the forum that you have to install this thing called Fire, either by pip install Fire or conda. So you might have to do that in your Colab environment.
Okay, that's very helpful. I'll give that a try. Thank you.
But I wonder if anybody else can help Christine if they have any experience, because maybe one of you has done this before.
Yeah, I think the advice I would give is it doesn't really help a whole lot to be able to import the stuff we previously wrote. So I wouldn't stress about it. Like it's, I think, kind of complicated to work in those environments. And so if there's code from another notebook, probably the easier solution is just to copy it over into a cell in the new one.
But it's so nice to not have to do that. But so I mean, if it doesn't, from my point of view, is if you could make this work, it's worth it because it really saves a lot of headaches. You're right. I mean, you can copy the notebook and import it that way, but that's kind of cumbersome. But I really think it has to do something to do with Fire. That's my hunch. Anyway, any other questions?
Yeah, hi. I do have one. It's related to what I'd asked in the chat about GitHub for these new courses. What is the correct way to get these notebooks in correctly to your local environment? I mean, I can clone that course v3/tree/master/NBS, so the notebooks are then going to go in a different place from the notebooks folder that we have for part 1. I'm just not sure how to do this sort of in a correct way.
Yeah, I mean, I guess you should just designate some place on your local machine where you want the new notebooks to go in. What I did was
yeah.
Well, yeah, what I did was I just wiped out my previous Fast.ai, my previous installation of Fast.ai, and just started all over again. I just installed it because, the new notebooks have been twiddled with and stuff, so I want to make sure I get the latest ones.
Right, but aren't these new ones just like, 8, 9, 10, 11, whatever? They're not 1 through 7.
Oh, right. Yeah, you can install the 1 through 7 as well. I mean, I think that, let me see, there's this page where, bookmark it, of course, getting started. There's a place, let's see if I can. Sorry, I'm just sort of looking for what I remember. There's this, can you see what I'm doing? I'm scrolling through this page now. Is that being shared?
Yes.
Okay.
Yep.
So yeah, this is the official GitHub Fast.ai install page, and so installation page. So it tells you, first you got to, of course, install your Anaconda and your GitHub, and then once you've done that, that's where this page takes over. Okay.
Yeah, I can go through this. I guess it doesn't. I guess do people think it doesn't really matter? I mean, you can. I would sort of have this feeling like, well, I don't want a new NBS, a new notebooks folder, but I guess it doesn't matter.
Yeah, I mean, if you can design a structure that makes sense for you, that's probably good.
Yeah.
Yes,
Okay. Thanks.
The new notebooks are DL2, right? So that should be fine. So the Fast.ai course v3, you have notebooks, and then you have DL1 part 1, and then DL2 folder, and that's part 2, and that's fine. I just clone the whole v3 course v3 repo.
Yes.
And then it works. So I just
Yeah, what I did was I first wiped out my previous installation, and then I, like you said, I cloned course_v3, and then I cloned Fast.ai, and then I cloned Hairbrain for later on because Hairbrain has the Swift stuff in it. But I mean, for now, all we need is the course v3. That has all the stuff we need in it now. And well, you probably want the previous notebooks as well. So I think if you just clone fastai.git, that will give you everything else.
Yeah.
Yeah.
Anyway.
All right. Thank you.
Any other questions? Okay, I'm going to go back to this notebook that we were working in. Notebook. Oh, all right, so, so he goes through and talks a little bit about broadcasting, and there's a lot of stuff here. I wish I had taken the time to sort of annotate this, but you go through and do all the stuff that he does, and you learn by just executing each line, and you'll see what he's doing. So, so let's start. Let's just start at the beginning. So, scalar. Sorry, he's defined this tensor already, and there it is. And then here's a command that generates a new tensor with Boolean values that tell you whether each element is greater than 0. And so there it is. Now the first broadcasting, we add one, we add the scalar, and remember the broadcasting rule basically will expand this 1 into a vector of the same length as A, and that's added to each element. So we would expect to see 1 plus 10, 1 plus 6, 1 plus minus 4, and that's what we see. So that's the simplest broadcasting. Now he's got this, we start with this thing called M, which is a 3 by 3 array. 2 times M is, it's sort of trivial, but when you think about what's going on in broadcasting, it's basically expanding this scalar 2 into a 3 by 3 array of 2s, and then doing an element by element multiplication. So, so each element gets multiplied by 2, and then that's the result. Okay, so that's broadcasting scalars. Now, the next one is looking at vectors. So there's a vector, and this is something that's always, it's something that's hard for me, and I'm still learning it, but this thing about shape. So it's supposedly a vector, but look at its shape is just 3. And to me, when I see a horizontal vector like that, I think of its shape as 3, 1. But it doesn't get that way unless you make it that way. So when you just generate that object, it has a shape called, it's just a shape of 3. So then we look at this M again, look at their shapes. So this is a 3 by 3 array, and this is just a 3. It's an object or something of size 3. But now when you add these things, let's see. Okay, so when you add these things, it automatically, implicitly says, okay, you have a row. This is a problem for me. I think this should be 3, 3, 1, but this is what it says this, that it says that this C thing is basically a row vector. Implicitly treats it as a row vector, and it says that when you want to add it to this 3 by 3 array, you expand that row vector by duplicating it 3 times, and now you have a 3 by 3 array, and then you add it. So in other words, you add 10, 20, 30 to each row of this. So we would expect this to say, 11, 21, 31, and then again, we're adding 10, 20, and 30 to each element. That gives you 14, 25, 36, and so on. Does everybody see how this is working implicitly? It's basically saying, if you want to add M, which is a 3 by 3 array, to C, which is basically a row vector of length 3, implicitly, what we have to do is copy that row vector 3 times and make it into a 3 by 3 array, and then we can add the 2 3 by 3 arrays. That's how I make sense of that. Does everybody follow that? And adding them in the reverse order should be the same. It shouldn't do anything different, and it doesn't. So, and what Jeremy says here is we don't really copy those rows, but that's what I think of in my mind when I think what it's doing implicitly. It has a faster way to do it. So let's see. Okay, so T must have been I'm not sure where we defined it. It must be this row vector. And then there's this torch command, I guess it's called expand as m. And since m is 3 by 3, I see. If we go c dot expand as m, it's going to make this object that I was thinking about. Remember I said when we're adding this 10, 20, 30 row vector to the 3 by 3, it's implicitly adding this, this 3 by 3 matrix to it. That's what it's implicitly doing. Okay, but Jeremy goes to points out that it's not really doing that. It's not really expanding it, but to a 3. It's not really expanding the row vector into a 3 by 3, but it acts as though it's doing that. Okay, and then he shows that T, which is this thing here, is being stored. You don't need 3 by 3 to store it. You're only, it knows somehow that it's the duplicate of, that each of these is duplicated. So T.storage, it only needs 3 numbers to store it. Let's see. And then he talks about stride and shape. T.stride. Okay, so T is this thing. Stride and shape. So shape I understand. Stride, I'm not so sure about. Stride tells you how many steps you skip when you, I'll have to come back to that. I think, I'm not exactly sure what this stride is. I'll have to come back to that. Unless anybody can mention that. Can anybody explain that, what that stride means? Jump in. Okay. All right, let's keep going.
Is that,
Well, I know from,
Yeah.
yeah, I was just going to say from CNN talks, he said that, you know how you take like 9, you take 3 by 3 pixels and you sort of move that window across. So if you have, say, I don't know what, say you have, doesn't matter, 10 by 10 pixels, you take that block of 3 by 3, and you move it 1 over, and then you move it another over. That's a stride of 1. And then if you skip, that's a stride of 2. So you move it, instead of taking the upper left 9 pixels, you're going to go across that first ray, and you jump 2, and then you jump another 2. That's a stride of 2 in CNN. So it must be something similar here.
Okay, so it takes this T thing, and I think the stride 0 means don't move in don't move any rows. So that's the 0. So it means copy this and stuff it here and then here. The 0 means don't move downward. So we're just taking this thing, and it has something to do with that fact that we're duplicating these 3 elements. We're not moving in we're not moving downward by any rows. We're just staying with that row and duplicating it. That syntax is a little, I'll have to think about it some more, but it supposedly makes sense. Okay, now there's this. So Jeremy is, he was all up in arms about how, people come in to deep learning and they get blown away. They try to read papers and they get blown away by all the Greek symbols from all these elitist mathematicians to try to keep you away from understanding deep learning. So, so go ahead and learn the Greek letters and so on. But to me, the Greek letters aren't a big deal. It's this kind of stuff that's a big deal. This unsqueeze and this syntax that he's using just very cavalierly that we have to really learn if we're going to understand it. So, so let's try to go through this and understand what he's doing here. C.unsqueeze. First, let me just, okay. I'm just going to remind myself what C is. Let's just look at C. So it's this tensor. So C.unsqueeze 0 makes it into this. I guess now it's got a different shape. Let me see if I do this. C.shape. And it'll tell me that the shape is size 3. But now if I go, if I ask for the shape of this guy, let's see what it says. So what it did was it converted this thing into an array with actual. This is kind of like to me this is a recognizable one-dimensional array. You know, it's a one-dimensional row vector. The first dimension, it's 1 by 3 row vector, right? So unsqueeze sort of gave it that extra dimension. Does that make sense to people? So unsqueeze on 0. I don't think. Oh, I wonder if I needed that. Let's see if I just do this. Nope, it needed that. It needed the positional argument. All right. All right. So basically, this unsqueeze command converts this this object into a bona fide row vector.
Hey, Joseph,
And yes.
Can you do unsqueeze 1?
Yes, that's what happens next. And
Okay.
Unsqueeze 1. So unsqueeze 0 sort of expands it into a row vector, and unsqueeze 1 expands it into a column vector. Can everybody see that? So those are useful things to have. And again, here's the shape. It's a 3 by 1. Okay, so let's see. Here's the. I guess we've already done this stuff. We've already. This is just Jeremy using this to play with, and you know, you can, as you go through the notebook. This is what I do when I go through notebooks. I just insert these new cells and ask questions and try to figure out what's going on. And Jeremy's done that here, so you can see. So without doing anything, the shape is 3. If you unsqueeze along 0, the shape is 1 by 3. If you unsqueeze along axis 1, the shape is 3 by 1. So that's good. Now, let's see. Now he shows it. I guess it's a different way to do the same thing. By inserting this none, you're getting the same thing. See. So let's see. Yeah. So there's different ways to do the same thing. So here's what he just did. If you go C of none, and then look at that. Oops, C of none. Oh, I put a wrong bracket. Sorry. Okay, so there's C, but you can see that now it's a 1 by 3. You could ask for the shape. It's 1 by 3. So it's another way of doing the same thing as unsqueeze does. So 1, 3. Yeah, and then if you do C of I guess there's 3 things that he does. The second thing is this one. You insert. I'm going to insert cell underneath. This in there and run it. So
there was a question in the chat about what if you did unsqueeze 2?
Okay, let's try it. I don't think it would work because, well, let's see. Maybe it will. Let's see. Let's try it. See how unsqueeze. Let's try that. Outer brain. Okay. So I guess it's because, well, why is it C? Wait, when we started, C was just, it just had 1 dimension, right? And then unsqueezing it along 0 means unsqueezing it along a row, and unsqueezing it along 1 means unsqueezing it along a column. I'm not sure what unsqueezing it along 2 would mean. Anyway, it didn't like it. But
there was also another question about that it might be helpful to get some quick coverage of why we're even looking at the matrix multiplication with regard to machine learning.
Well, Yeah, so you all remember from when we apply, when we do forward propagation, we're always multiplying weight matrices by activations. So it's the whole thing is all multiplication, is all matrix multiplication. So it underlies all of machine learning matrix multiplication is basically the basic operation that underlies everything we're going to do in machine learning. So that's why I think that chapter 8, the word that keeps coming to mind is infrastructure. We're sort of building infrastructure for the rest of the course by implementing matrix multiplication, by getting the notebooks up and running on whatever environment you want to work in. Yeah.
Hey, Joseph, quick question. So did he talk about why we need unsqueeze? So I thought like broadcast would handle all our needs, but there might be some cases you need to do unsqueeze. Like
Yeah.
I
Sometimes, just for example, the examples we're looking here. Suppose you need to make something into a column vector. Well, this is a way. You have a row vector, you want to make it into a column vector, then this is the thing, the unsqueeze, or this is an equivalent.
Okay.
So unsqueeze 1 is equivalent to this thing here, where you put none in the none in the new place where you wanted to insert a singleton dimension, right? So it takes that C, which had just a dimension 3, and then it inserts a 1 where you put the none. Now it has dimension 3, 1. So,
Okay. Thank
yeah,
you.
does that make sense? Yeah. And also, it's nice to be able to, it's nice to see that the broadcasting works, but this helps us to see how it works.
Okay.
Let's see.
Makes sense.
And there's this. So there's this other syntax here. 3 triple dots. It just means everything else that went before. So if you have this, 4-dimensional matrix, and you don't want to specify all the dimensions, you can just put these 3 dots there, and you can just focus on the last dimension. All right, so matrix multiplication with broadcasting. Here's the next one. Remember we had this inner product replaced by a dot product. This is my dumb comment, so don't pay attention to it. So here's what he does. He says, you're multiplying these 2 matrices A and B. Take A, row I of A, unsqueeze it along -1. I believe that makes it into a column vector. So this first thing here, A of I, you have this, 5 by 7 matrix. I don't know what the dimensions of it is, but A of I just picks out that row, the ith row. And then unsqueeze of -1 means add a new dimension at the end, which makes it into a column vector. So if you just said A of I, it would be a row vector, but followed by dot unsqueeze -1, that makes it into a row vector. Sorry, it's A of I is a row vector, but followed by dot unsqueeze -1, that makes it into a column vector. Does that make sense? And why is the -1? Well, -1 means the very last dimension. I think it would work the same if you put unsqueeze 1. But anyway, so what is that doing inside? It's taking this column vector, this thing that we've made into a column vector, and then using broadcasting, it's multiplying it column by column with this matrix B. So it's multiplying every column of matrix B by this column. Does that make sense? And then it's adding them at the end. So that is that's equivalent to, let's see, that's the new, let's see, that's the new row I of the product matrix. So let me think for a second. So before we thought in terms of row I and column J, we constructed the ijth element back in the previous method. We constructed the ijth element by taking a dot product. But now we're taking, sorry, let me go back up here. Okay, this is the That's the 3 loops. We got rid of that. So we did better than that. This is, in this one, sorry. So here we construct the ijth element by means of a dot product. So that was the second refactoring of the multiplication. Now we're doing it a third time, and what we end up doing is, instead of constructing the ijth element, at a time, at once, in each operation we construct the ijth element. In this method here, we construct the entire ith row. So basically, this makes a whole row of dot products. Does that make sense? So you're basically, I wish I could draw this out on a piece of paper. Maybe okay. This thing here, a of I dot unsqueeze of -1. I claim that makes the ith row of A. It just takes it and flips it into a column. Okay, everybody following that part? You take the ith row of matrix A and make it into a column. Okay, and then the broadcasting step is you multiply this column vector by this matrix B, and broadcasting checks that the column vector has the same length as the number of rows of B, which it does, because we already know that the number of columns of A is the same as the number of rows of B. So this a of I dot unsqueeze of -1, this column vector, can be multiplied by B, and we multiply it column by column. So the first column of B gets multiplied by this thing, then the second column of B, and then the third column of B, and so on. Is everybody following that? And then by taking dot sum along dim equals 0, that means along the vertical direction, we are creating dot products in every we're running all the dot products at the same time. I don't know if I'm making myself clear. So when you take a dot product, you basically take two vectors and multiply them together element by element, and then you sum them, right? That's a dot product. So here we're doing that. We're doing this. We're taking a vector and we're multiplying it element by each column of the matrix B. So, and then we sum along the vertical direction. That means we've got a dot product in each of the columns. We've made a dot product for each column of B, and that gives us the whole row C of I all at once. And so that turns out to, I'm not sure I did a good job of explaining that, but I tried. Anyway, so that's another speed up, and now it looks like we got a speed up of a factor of 3 or so, because we had like 1 millisecond. What was the speed of the last one? Way back up here. Yeah, 2 milliseconds, and now we have microseconds. So maybe a 5 times speed up. Yeah. And let's see. And then, so the final one, we're already at the end of the lecture. So the final one is this Einstein summation, which makes things go even faster. And the idea is it's a construct. It basically tells you to do what you would do if you multiplied 2 matrices together. You're going to take the ith row and multiply it by the jth column, and for each element. And that's what this little script text is telling you to do. So this command einsum of AB says take these 2 matrices AB and use this Einstein summation convention to sum over the kth dimension. So that is it basically multiplies the ith row times the jth column, gives you the dot product with the ith row and the jth column. And it's a very quick way to do it. So if we do that, and then we time it, we find that we got, well, somehow it runs slowest the first time. We got another factor of 5 or more in speed up. So the idea is that we've successively refactored the matrix multiplication to make it extremely fast. And Jeremy says he speeded it up by 50,000 times from the dumb Python way to do it. And then the finally, there's a even faster way, and that is, I think when you do it, well, when you use Torch, I think you're implicitly using the GPU, I think. So I thought that was why this one got even faster, but so I'm not sure why this one goes faster. This is PyTorch's intrinsic method of multiplication, which is if you want to multiply two matrices, you go m1.matmul of m2. So we got another factor of, I don't know, 7 speed up. So basically, going through this one, we have refactored multiplication, a matrix multiplication, to make it really, really, really fast. And from now on, we get to use it. We get to use fast matrix multiplication in our lessons from now on. And then here's that command I told you about, where you export this notebook so that you can use it in the next one. And so what it just did is it wrote this notebook nb_01, which is this notebook translated into a Python module, and it saved it in this directory exp. And there it is. So I'm going to just quickly go back to the PowerPoint and share that. Let's see. Share. And, sorry. I can't find it now. Anyway, sorry. The idea is for next week, you should go through the rest of the lecture, which is, I think, roughly from an hour and 10 minutes onward. And then the notebook that they cover is the second is notebook 2, and it goes through forward and backward propagation. And then Jeremy also suggested that we read this paper, at least part of this paper, on I can't remember the name of it right now. I had it written down. Anyway, I'm going to post my notes, and that has the name of that paper that we're supposed to look at. Okay. Well, thanks everybody. Are there any questions before we quit? Okay. I'll leave because I think some people might want to go to the NLP course from here. And thank you very much.
Yeah, thank you, Joseph. That was great. Thank you.
Okay.
Thanks, Joseph.
Thank you.
Awesome job.
Welcome.
Thank you. That was great.